Okay. Okay, so quickly. Again, we are trying to make a visual of being able to monitor the production of P particles as the time passes. Time equals T equals 0 seconds, 5, 10, and 15 seconds. So initially, we have a lot of reactants. These are reactants A. There's a lot of reactants initially. Of course, over time, the reactants disappear. They become P particles. So over here, we have a lot of A. And over here, we have a little of A. A little of A, okay? Is the word a reactant, okay? Okay, so initially, there are no P particles. So we're trying to watch P form. And then all of a sudden, bam, P. A lot of P's are made. Rubin, how many P's are there? 7 P's. Okay. And then as time goes on, let's assume we have 9 P's here. And here we have 10 P's. Okay? And of course, if we wait any longer, no more P's form, okay? So, last time we saw that the rate is equal to the change in concentration. Here P, we're looking at P, concentration of P over change in time. Okay, so as the time is going on, P is increasing. The volume here are the same. This is the same reaction container. The ink is erasing itself. So, let me ask somebody really quickly. Let's go do Zoe. This is the same amount of time as this. From here to here is the same amount of time as from here to here. And here to here. What can you tell me about the rate? The rate is decreasing. Very good. So what we're seeing here is, look how many P's are being formed here. From here to here, how many P's are formed? 7 P's. 7 P's over a time of 5 seconds. And over here, let's go back to Zoe. Over here, how many P's have formed from here to here? 2. 2 P's formed over 5 seconds. And here, 1 P over 5 seconds. All right, so look at the change in P over the change in time. So we can see that it's really fast in the beginning. Pa-bam! And then slower and slower. So graphically, we see this thing. Time on the x-axis, concentration of P on the y-axis. And this is something forming over time. So initially we have 0 P's in the beginning. And then the first 5 seconds, 10, 15, and 20. What we're seeing that it's a fast, sharp increase and then slows down. So you're right, Zoe. This thing slows down over time. These are my 5-second intervals here. Of course, we're human, so we can't really see the very time. We can't see milliseconds here. So this graph, even though it looks like straight lines here, it's actually just a curve. Obviously, you can make that out. Yeah. All right, my ink is erasing by itself again. Again, same axes here. All right. So let's continue to look at what we did last time. Now let's do this. I'm going to ask you guys a quick question. I'm just going to put concentration here of some A going to B. Okay? I'm going to draw a few curves here. And I'm going to ask you guys. See if you guys know what these things mean. So let's have this guy. Let's have this guy. Let's have this guy as well. And let's have this guy. Oh, we have a few curves here. We have A. Let's do curve 1, 2, 3, and 4. For the reaction, A goes to B. Okay? Let's go to Rubin. No, I have to pick you already. Let's go to Faith. Faith, you're this one? Okay, Faith. I am looking for, this is C concentration, okay? A is turning into B. I want to know which curve here belongs to A disappearing over time. A is disappearing over time. Which curve is A disappearing over time? Huh? 4. She says 4. Okay, and that is correct. is disappearing. That's a reactant disappearing over time. Please note that over here we were monitoring a product forming over time. Hence, those products are forming over time. A is disappearing, and you're right. Here, you can see that it is a fast change in concentration per unit time, and then it starts to slow down because these tangent lines show us that the rate is also slowing down also. Rate is always slowing down in a chemical reaction. Real fast in the beginning, and then starts to slow down over time. All right. All right, I've asked you guys questions. All right, next thing. I want us to recall the rate law. This is from last time. I need you guys to write the rate law. I need you guys to put your name on top of this little piece of paper. Okay, pass that back, please. All right, everybody has a piece of paper. Please put your name on top of there. I'm going to write a few generic chemical reactions. You're going to write the rate law for them, and you're going to also solve something else for me. Well, we'll see about that. So first, I'll give you guys some chemical reactions. All right, the first one is A plus 2B goes to C. I need you to write the rate law for me for this one. That's number one. Number two is next. Let's do C plus A goes to C plus, let's do E plus D. And then number three, 2A becomes C. So these are generic chemical species, A, B, C, or D, or E. And I need you to write the generic rate law for me here. Put your name at the top, please. William just taught me how to use this machine. Thank you, William.
Which machine?
This machine that makes you sick.
You're using.
Yeah. Okay, you guys should be done now. Let me collect these. Again, you need to put your names on these. Pass them forward, please. All right, so just quickly, the way you write the rate law for these, you only put reactants in them. You simply write out the word rate, because that's what we know that the rate is dependent on the reactant concentration. It is equal to some rate constant K, the reactants A and B, and we don't know the orders, X, Y. We're going to solve for those today. For this one is next. Rate equals K, B. Reactants A, B. Reactants here are C and A, okay? Notice that the coefficient 2 here is not put as an exponent here. That's a common mistake. Rate equals K and A to the X. C, A, A. Any questions here? Uh-oh.
That A is a separate equation.
C and A are, okay, so these are all separate problems. These are not sequential problems. What is your question?
You need to put Y.
I do need to put Y. I forgot that. Thank you, Judy. I was just checking to see if you're paying attention. That's just how I do. All right, let's take a look here real quick. All right, we're going to make some people lose their faces. All right, Angela. Good. Catherine. Good. Kevin. Okay, you guys are all good. Deshane, good. William? Okay, good. All right. You like don't have some equal signs here. On a real test, you don't put rate equals, that's not okay, right? You need to put that there. Okay. All right, not bad, not bad. You guys know how to write the rate law, use the rate law. I'm gonna kill this real quick now. Okay, now, next part. I need you guys to solve for something for me. Sometimes the units of the rate can change. So sometimes, for example, if I am driving a car at 30 kilometers per hour, I can put that in meters per minute if I want. Okay, so sometimes something is changing. So for example, we have iron. Some element iron is forming at the instantaneous rate of, let's do 5 grams per minute, okay? So somebody is making iron. We have a lot of iron on this earth. We need to use it. We have bridges, buildings that are made out of iron. So we're extracting iron, and in this process it takes 5 grams per minute to be formed. I need you to calculate how many moles per second that forms. Question mark. Please do that on your note papers right now. I see some people looking at on the periodic table. That is good. Vivian, what is the molar mass of iron?
55.8.
All right, that's going to be an important piece of information. Favorite student. Am I putting too much pressure on you? Let me see, Ali. Good. Good. And good. 5 grams. I think you need to work on that. Switch that. This number up here is mass. This down here is mole, so it's 56 grams per mole. Okay. Yes, you do need a calculator. That would be nice. Okay. Let's take a look up here really quickly. This number here, you should, it's a unitless number. But you need to think of it as a gram per mole, okay? So there are 55.8 grams of iron per 1 mole of iron. Remember, a mole stands for a lot of number of particles, and we're not interested in the mass of 1 iron atom, okay? So they designed this system of a mole to help us understand what a large amount of atoms are. It's Avogadro's number of atoms. Okay, but anyways. So what you really always do, number 1, write down what you have. I have 5 grams per 1 minute, okay, of iron. For every 55.8 grams of iron, that's going to give me 1 mole of iron, okay? After that, I have this 1 minute problem. I need to turn that into seconds. So for every 1 minute, there are 60 seconds. And then you would need to punch this out. What was the answer, Deshaun? and this is in moles per second. Please understand, this number makes no sense to us. 1.5 times 10 to the negative 3 moles per second. That doesn't make sense very much to us. But in chemistry, we like to work with the mole. And this makes more sense. We're pumping out 5 grams per minute. So that's why it's important that we know both. All right? Please make any corrections. All right? This should be something that you can handle. Again, this is like turning feet per second into kilometers per hour. It's the same idea. You guys should be able to do it in physics. You should also be able to do it here. Okay? So again, write down one. Write down what you have, and then use the conversion factor. These are both conversion factors. All right. This is done now. Okay. We're going to now move on. We're going to go forward now to looking at solving for orders. Recall we just did here. The orders are these x's and y's, these exponents. Okay. These exponents are the orders. All right. So please pay attention because I'm going to throw a lot of stuff at you, and then I'm going to ask you guys questions. Maybe. I don't know if we have enough time because I still want to do lab stuff. Anyways, so again, if we look at time and concentration of a product, okay, this is concentration of a product forming over time. So you're going to see an increasing value. So if we have a high concentration, high reactant concentration, so let's just, again, I'm going to use the simple A goes to B, all right? And we're looking at B form. So this is the concentration of B on the X and Y axis. On the X axis is time. We know that the reaction decreases over time, okay? And that's a high amount of it. This is using a high concentration of A. If I use a high concentration amount of A, I have a very fast rate of reaction initially, okay? Initially. Notice that initially it is relatively constant. That's a trick that we're going to use today. Now, if I decrease the reactant concentration, then what happens is this initial rate starts to decrease. Okay, so now this is, I'll just say high initial concentration of reactant, low initial, or lower, let's just say medium, okay? Again, I just want to use these simple terms so that we can kind of get an idea of what's happening. Of course, I can use also a low amount of reactant, okay? If I use a low amount of reactant, then I will expect a lower rate of reaction also, a lower initial rate of reaction also. Okay, so this is a low reactant concentration. I'm using a lower initial concentration of A here. So these slopes, these initial slopes, these tangent lines that I drew earlier on, I can get those slopes and I can plot those against concentration. So these slopes are the rates, hence they are now the y-axis over here. These slopes are now the y-axis of this. And this is concentration of B forming over time. Again, if I use a high amount of reactant, I have a faster rate of reaction. And if I decrease that initial amount, I have lower rates. So I can now put my initial reactant concentration down here. And quickly you'll see that if I start to increase this, the initial rate, I'll put a little I here so that you guys know that these are initial. But you'll just see that they're increasing. Okay? So again, these slopes, these initial slopes, that's here now. Okay, so notice that at high concentration, way over here, I have a high rate. Okay, so this rate here is very high. It's a big slope, hence it's high. It is the high concentration A initial. Obviously, if I have zero reactant, then I have zero rate, obviously. So what I'm saying here is that you'll see that I have a straight line here. This here is very important. From this information, you should know that this is a first order, which means that the exponent here, if I write the rate law for this, is rate equals K raised to 2. We don't know what x is, we just solved for it. It's a straight line. X equals 1, okay? Alright, so my marker is being erased by the previous clean here. Alright, so graphically, what we just did, transferred from concentration changing over time to rate versus concentration, and I just plotted this curve here. It's a straight line. Our y equals mx here, where the intercept b is 0, okay? Y equals mx. X is equal to 1. Alright? So it's a linear. It's linear. If you see a linear graph of rate versus concentration, then that means you have a first order rate reaction. Come in! You're a little bit tired. Are you tired? Or am I boring? Alright, it's okay. It's okay. I think I've woken you up a little bit. Do you understand this though, Kevin? Alright, so Kevin, if x equals 2, what can you tell me about this? The initial rate as a function of the initial concentration of the reactant. If x equals 1 and we get a linear graph here, what if x equals 2? Huh? Parabola, come draw it for me. I want you to write the rate law for me right now. With x equals 2. The reactant is A goes to B right here. Okay, good. Now if you plot rate on the y, and this is my blue towel. Go ahead and use a blue towel. Alright, I'm on time now, so we need to move. Okay, that's a beautiful graph. Thank you very much. Kevin, let's go. Let's go, Kevin. Let's go, Kevin. Okay, so what's going to happen is we're going to get plotted data points that look like this, and it is going to be a parabola. This looks like y equals mx squared. M is just a constant, our unknown here. It's just a parabola, okay? So basically, when we look at the concentration of B forming over time, the slopes, the way that they change, are like this, instead of a straight line. Hence, from this graph, you should be able to tell me if it's first order, second order, or zero order. Let's look at a zero order. So, what did we do here? What we did was, our rate law, which is here, now it's been erased by the former. Our rate law here, we didn't know how to solve for this x here. It's unknown. Given if we do enough experiments to plot this out, we can determine that if the graph looks like this, it's x equals 1. If the graph looks like this, it's x equals 2. And finally, there's also a possibility of the rate equals k, reactant concentration raised to the 0 power. Anything raised to the 0 power is 1. Rate equals k. Okay? So in this case here, if we're looking at how the rate depends on the reactant concentration A, the initial reactant concentration, we will see that it's just a constant. Okay? And of course, these are plotted data points, okay? It's not a continuous line, it's a data point. You guys get this? Okay, so let me check really quickly. Let's do qhia. Qhia, if this is the some reaction, A goes to B, let's do it like this, to see if I can trick you. I have this here, and this is the rate. And I have a bunch of data points, and I have this here. What order? Okay, so they call that first order. If x equals 1, they call that first order. Okay? This one, if x equals 2, second order. And finally, 0th order. Okay? Let's do one more. Let's do crystal. Crystal. If I plot the rate, the initial rate, as a function of the initial concentration A, and I get this curve, what do you think it most likely is? Yes, this is second order, good. It looks like a parabola. Second order. And this is first order, because it's a straight line. Alright, these curves can often get mixed up a little bit. Please know these. I know what, Jack, you're probably thinking, well, how do I know if this is a second order curve, right? Well, is it how? Because you know what? Y equals x cubed looks similar. That's what you're thinking, right?
Yeah.
X cubed looks kind of like x squared, right, Jack?
Yes.
So what if it's third order? All right, it turns out that a lot of chemistry reactions do not follow third order kinetics. Okay, they only follow 0, 1, and 2. In any case, AP only goes up to 2, so you don't have to worry about x equaling greater than 2. Okay, sometimes x can be a fraction, like a half. Okay, sometimes. Okay, so you're only left with 3 options: 0 order, first order, or second order. All right. Now we're going to do another way to, now we're going to do one more way to solve for the orders. So what, and then after that, I'm going to hit you guys up with a demonstration up here, and then we got to move quick though. I'm going to do it up here. I'm just going to do it once, and then we're going to move to the demonstration, because I really want to get that done. Alright, so the next thing, we have just solved for the orders looking at graphs. So this is sort of a graphical approach, okay? Now, the approach we're going to do next, we're going to use some math and we're going to use some experimental values to solve for the orders. I have 10 minutes left. I'm going to hold you guys 5 minutes, okay? Alright, so I'll just do this quickly, one example, and then I'm going to do the demonstration. So, here we go. We're going to do some experiments. And for some reaction, A plus B, notice that I have 2 reactants now going to some product C, and we're going to monitor this reaction. And I'm going to do some experiments, 1, 2, and 3. And what I'm going to do is I'm going to look at the rate of reaction. I can look at how much C is forming over time. That's perfectly fine. So the change in C over change in time. Okay, that's this column. So what I do is this. I look at some reaction happening over time. I start the time when I mix the chemicals together. And I stop the time when the reaction completes. Okay, so that's how I'm going to obtain this rate information here. So this is rate here. Notice that rate will have units of molarity per second. Also, what I'm going to do is I'm going to look at this A and B here. I'm going to vary the initial concentrations of A and B. Alright? And what I'm going to do is, I'm just going to choose easy numbers so we can do this quickly, but I'm going to say that if I have 1, this is, the units here are molarity obviously, those concentration values. So here's 1 molarity, this is 1 molarity. What I'm going to do is I'm going to keep B constant. In the next experiment, I'm going to keep it constant, but I'm going to increase the concentration of A, the initial concentration, by 2 times, okay? What I'm going to do is I'm going to observe the rate here, and I'm going to put in a number. Let's just say it is 4, okay? C is forming, the change in concentration of C forming per unit time seconds here is 4 molarity per second. As I increase A from experiment 1 to experiment 2, I notice that this also increases. That makes sense, okay? If you have more reactants, we should have a faster rate of reaction. All right. And in experiment 3, what I'll do is, in this case here, I will keep A constant. So here, 2 to 2, I'm going to keep the A, 2. If I look at experiments 2 and 3, notice that I keep A constant, and I want to see how B affects the rate of reaction. So I'll double that this time, okay? And when I do that, I realize that it is 8 again. All right? So, with this data here, we can solve for the orders. All right? And this is how you do it. First off, you have to identify the experiments that are important. Identify the experiments that are important. I purposely kept B constant here, so I don't have to deal with B. If I write out the rate loss of this is rate equals K, concentration of A, unknown X, B, unknown Y. Okay? I kept B constant so that I can focus on A. So when I'm going to first, now I can rewrite the rate. Looking at experiments 1 and 2, the rate will equal K, A. B is out of the question now because B is not affecting the initial rate. B was kept constant, looking at experiments 1 and 2 only. What I can do now, it's simplified now. I can use this equation. I can take the rate of the first experiment and divide it by the rate of the second experiment. If I do this, the numerator here equals K times the concentration of A from the initial experiment of the first experiment to the second experiment. Notice that K cancels out. This is very important. Alright, and of course these two are raised to some power x. Again, rate, we have these values. It's sort of a math trick, okay? I'm taking each experiment and I'm dividing them by each other. So here, we have rate 1, that's 4. Divide by rate 2, that's 8. Equals, the k's cancel out. I have A from the first experiment equal to 4. Here, 8. Alright? Of course, I can take x out. What is x? Angela, what is x? X equals 1. Alright? So this is the first order here. So we have just found this out we just found x. Now we can do b. Now I have to compare experiments 2 and 3 this time, okay? Because a is kept constant, and now I can solve for b. So now we have this equation, rate equals k, b, y. Alright, so if you guys do feel overwhelmed, don't worry. We're going to go over again this next week, or next time. I have to go through this a little bit quickly though. If we don't have time to do the experiment back there, at least you guys will see me do it up here. Okay, now, again, we chose experiments 2 and 3 because A is kept constant, so it's not affecting the rate. We're going to see what happens here. We're going to do rate of the experiment 2 divided by rate of experiment 3 equals K. K. And the concentration of B2, B3. And these two are raised to some y power. Again, you'll see that the rate is not affected. 8 over 8. K's cancel. And we have 1 over 2. What is y, Kuma? No? Yes, y equals 0. Alright, so now we can write the overall chemical reaction. The rate here equals K, A, X, B, Y. We have found out what X was. It is 1. We have found out what Y is. It is 0. So now the overall rate of the reaction is this. Alright? You guys got that? So the math trick here is dividing the rates from each experiment. Okay? Okay. Again, we will look at this in more detail next time. Alright. So, what I want to do now, is it hot? I'm really hot. Your cheeks are red, Angela. Alright, so again, I don't think we're going to have time for you guys to do it back here. If some of you guys want to wait just a little, you can do that also. But, Alright, so what I have here is I have the chemical set up here. You guys can focus on the screen. And what I'm going to do is I'm going to add some chemicals together. Okay, and the reaction of interest is, well, why don't I have you guys turn to this certain page first? Or turn to page 63 in your lab books. Page 63 in the lab book. Alright, so if you guys are looking in the lab book, what you'll see is an equation at the very top. You'll see that there's going to be a solid forming over time. Sulfur solid is forming over time. Can you guys see that? Alright, so when I add these reactants together, we're going to produce this solid sulfur here. Okay? And that solid sulfur is going to form, and I'm going to be able to see that. When that thing is forming, what's going to happen is I'm going to observe it form to a point. Okay? So watch. Let's do this. Deshaun and Jack, you guys might not be able to see. According to this, okay, so he's gone. This is what I'm going to do, okay? I have some Na2SO4, S2O4, okay? I have some water, and I have some sulfuric acid. Okay, your concentrations are listed in here. And what I'm going to do is I'm going to add different amounts of these together. The first one is going to be, I'm going to use 45 milliliters of this, 0 amount of water, and 10 milliliters of sulfuric acid. Okay, this is volume. And then the next experiment, I'm going to do 20 of this, 25 of this, and 10 of this. Notice that the sulfuric acid I'm going to keep constant. The total volume here will always be 55. Total volume for all of these is 55. I've done that so that I can control the amount of concentration of this. Notice that here I'm using the full amount of the sodium thiosulfate, and here I'm using less and I'm adding water to it. I'm diluting it here, okay? We're going to see that the rate of reaction is slower for these. 10, 35, and the next one is 30, 15, 15. Okay, so this one has the lowest amount of concentration, okay? This is what I will do, teacher. Okay, I'm going to do the one with the lower amount of sodium thiosulfate added with water, and then this. So why don't you guys pay attention up here onto this big screen over here. So what I'm going to do here is my graduated cylinder. I am going to add 10 milliliters of the sodium thiosulfate. That's here. I have the concentration as well.